Hello everyone. Once again I welcome you all to MSP lecture series on interpretative spectroscopy, and I am sure you are all enjoying the interpretation of very interesting phosphorus compounds and also their metal complexes having several other NMR active nuclei. So, let me continue with some of the molecules that I showed you in my last lecture. I showed you in my last lecture this molecule and then 3 spectra here, and the first one we concluded that it is due to 31P NMR, and the splitting pattern also I showed you. And just remember, now we have another set of signals here in the second one. Second one, if you just see 1, 2, 3, 4, 5, 6 are there, that means 4 multiplets of 6 lines each, and again in the last one also we have 6 lines and 4 multiplets are there, each one having 6 lines, but the spacings are a little bit different. That means they are not due to the same nuclei, they are due to the different nuclei. So, just let us look into them. Now, it is very clear that 31P NMR spectrum can be interpreted in this way by writing this coupling tree here. You can see first it is coupled with 3 fluorine atoms to give a triplet, and then each line is coupled with 15N to give a doublet here, and then each line of this doublets again split into doublet because of 2 bond hydrogen coupling, something like this, and then each line is coupled with 3 hydrogen atoms present on silicon to quadrate in 1:3:3:1 ratio, and if you count all of them, we have totally 48 lines, and that 48 line spectrum looks something like this. The original 1:2:1 ratio what we saw here is retained here, and then again if you see here these doublets are 1:1:1, that is also maintained here. So, now let us look into 19F NMR spectrum. It looks little bit complicated, but it is not really. So, then first of all we have to analyze how each multiplet has 6 lines here. Before that, let us start looking into 19F NMR. Assume it is 19F NMR, and at the end we can conclude about that one. And if you take here, if you consider 19F NMR, first that will be split into a doublet because of phosphorus coupling. So, this is the PF coupling here, and next this is coupled with 2 bond 15N, that is again each one will be a doublet here. This is FN coupling here, this is FN coupling, and then each signal of fluorine is coupled with hydrogen to give another doublet here. So, this is your 3FH coupling due to hydrogen that is present on nitrogen. Now, we have to look into 1, 2, 3, 4 bond coupling here. So, 4 bond coupling would be here. So, that would split each line into a quadrate. Because of the smaller spacings of FH, with the magnitude of that one is much smaller, what happens, first 2 lines of the second signal and last 2 lines will merge. As a result, what happens, the intensity of this will go up, and then same thing happens in case of all the 4 signals here. And you can see here they are merging little bit because of closer spacings and very marginal difference in their chemical shifts. It can show now 1, 2, 3, 4, 5, 6 are there, but intensity varies. Now, as a result, what happens, it appears like a sextet in each case. And then if the spectrum is given, sometime often we get confused why sextet is there. Each line should have been a quadrate, very similar to what we saw in case of phosphorus, but here it is sextet because these 2 are merging here. So, as a result, we get something like this. This is a typical 19F NMR spectrum shown here. Now, let us look into 15N NMR spectrum. Again, we have 2 options are there, whether which one is larger, whether NH coupling is larger or PN coupling is larger. Let us assume PN coupling is larger, getting some hint from the previous 31P NMR spectrum we looked into. First, this N will be split into a doublet. This is a PN coupling here, and then this will be coupled with hydrogen. So, something like this. So, now if you just look into it, now we have 6 lines are there each one. That means there is no individual splitting is there. That means basically 1 2 bond, 1 2 bond. So, fluorine is also 2 bond apart from 15N, and also silicon bound hydrogen atoms also 2 bond apart from 15N. That means totally if you assume the coupling constant is of same magnitude in case of both FN coupling as well as 2 bond NH coupling, then we have to count together. So, we have 1, 2, 3, 4, 5 equivalent nuclei are there. Then if you just use 2Ni plus 1 rule here, of course, all of them are with spin half, and we have 5 of them, half plus 1, it gives 6 lines. So, each one should be a sextet. So, that means we have something like this 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and the spacings are little bit different compared to what we saw in case of 19F NMR. So, the spectrum should look something like this. Yes, now we have the spectrum. Okay, so very easy. So, that means basically the 3 spectra that is given are for 19F and 31P and 15N. So, what is left is 1H. So, 1H I had left it for you people. So, you people try to sketch NMR spectrum of writing the coupling constant tree, splitting tree, and then just see how it looks like. And you can take about the couplings, you can take hint from these 3 spectral data. Now, I have given another compound here. This is cyclodiphosphoxane, and cyclodiphosphoxanes are 4-membered inorganic ring system, saturated ring system with alternate arrangement of phosphorus and nitrogen with phosphorus in trivalent state, and they can exist in cis and trans forms. Cis is more stable, kinetically more stable isomeric form conformation. And then the nitrogen is planar here because of the 2 pi electrons interacting with the sigma star of phosphorus, that we call it as negative hyperconjugation. As a result, what we have is 2 pi sigma star interaction. Because of that one, nitrogen lone pairs are delocalized here. As a result, the PN has multiple bond character, and hence this appears like a planar molecule having sp2 hybridization at nitrogen. So, when you react this one with appropriate metal reagents, either you can form binuclear bimetallic complexes or monometallic complexes, but it cannot chelate because of the planar structure, but it can only act as a bridged bidentate ligand, or if you use one equivalent, it can act as a monodentate ligand, leaving other phosphorus uncoordinated. We have one such case here, rhodium chlorocard dimer. When it is reacted with the 2 equivalents of cyclodiphosphoxane, what we get is a monosubstituted, monocoordinated compound of this type. Here we have card, cyclooctadiene is there. And now if you just look into it, this is a typical AX spin system in case of 31P. And now if you see this PX is directly attached to rhodium, and first it will split into a doublet. And then of course each line can further split into a doublet because of PP coupling. In that case, what happens, it will be, the values are very small and it would appear something like this. And whereas P is coupled with, PA is coupled with X to give a doublet, and then it does not show any rhodium coupling, otherwise it would have split into a doublet of doublet here again. You can see here that is rhodium phosphorus coupling of 229 Hertz. And then see, whatever the coupling we anticipated is not there, but when you, since we have one free phosphorus is there, you can again coordinate that one with another heteroatom. For example, when it is treated with AuCl SME2 here, this is reacted with AuCl SME2. SME2 is a very labile ligand, and SME2 goes off, and then what you get is here AuCl is bound. Now again we have AX spin system, both are coordinated. Earlier we have one free uncoordinated phosphorus. Now you can anticipate some sort of PP coupling comes now. PP coupling is coming here. In the previous one we did not see. Now the PP coupling is order of 30 Hertz, that you can see here. And also surprisingly, now phosphorus is coordinated to gold. It also shows rhodium coupling, that is 3J rhodium phosphorus coupling of 5.58 Hertz. And this one, what we see here is due to the complete substitution of both the phosphorus with gold. That means basically when this compound is treated with AuCl SME2, apart from forming heteronuclear compound, partly it has replaced rhodium also to form digold complex. That is what it indicates here. Some of this vital information you can extract when you look into NMR spectrum carefully. So it gives much more than what you are looking for. This is where the importance of spectral data comes into picture in understanding the reactivity and other things. For example, now if I start using excess of AuCl SME2, probably I should be able to replace rhodium also to form a di-gold complex. In fact, we have done that one in our laboratory some time back. So interpretation is easy, and also we came to know that suddenly phosphorus-phosphorus coupling is increased when both the phosphorus are coordinated. And it is now very interesting to look into the electronic situation at both the phosphorus with some theoretical background or calculation, DFT calculation and other things that might tell you why now PP coupling is very intense compared to the compound where only one phosphorus was coordinated. So this is for this one, as I mentioned here. So now one more interesting molecule is there. Again, this is a rhodium chlorocarbonyl complex having a phosphine imine ligand. So one phosphorus is directly attached to rhodium, and other nitrogen has phosphoryl azide is bound one. So we have 3 phosphorus atoms are there now. So that is like almost AMX spin system. And in this one, in first case where we have P, this phosphorus here, this is directly attached to rhodium. So it can first couple to give a doublet, and each line can be further split into a doublet because of this 2-bond PP coupling. So this one you can assign for P here. So this is the rhodium coupling here, 1J rhodium phosphorus coupling, and this is 2J PP coupling here, and this is farther, so this is not showing any coupling with this one. Now if you look into this one, it's a doublet of doublet. This may be due to this one here. This first couples with this one, and then this is coupled with this one also. It's a doublet of doublet here. So this phosphorus doesn't show rhodium coupling, whereas this one shows. Now only this one is left. Now this one only coupled with this one, so it gives a simple doublet. So that means now very nicely interpret the data and also check whether the compound is formed or not. For example, this ligand is taken when it's treated with the half equivalent of rhodium chlorocarbonyl dimer. Okay, so this is taken and then this is reacted with okay, so this is 2 equivalents we have taken, and then it gives the compound shown here. This compound is shown here. Yes, now we can conclude that this bond is broken and it is formed a mono rhodium compound in this case. Okay, now we have another interesting molecule here. This is a platinum compound of bisphosphine, where it is a unsymmetrical bisphosphine. One side it is OPPH2, other side it is NPPH2. And then if you look into the 31P NMR spectrum of this one, it shows 2 signals without any PP coupling, as they are 1, 2, 3, 4, 5 bond apart. So that means it doesn't show. When we make a compound with this one, say platinum or something, now through metal they can interact, because through metal they are only 2 bond apart. So if through the ligand framework they are 1, 2, 3, 4, 5 bond apart. So when they are 4 or 5 bond apart, it is less likely that they couple with each other. Instead they will show a singlet. But on the other hand, when a complex is formed, what happens now? They are coming closer through metal. You can anticipate through metal coupling. With this one, it's a very nice example where the phosphorus-phosphorus coupling is absent in the free ligand, whereas when it forms a chelate complex, now they are coming closer and they can show coupling here. That means it also gives some idea about when such molecules are there, how much the coupling one can anticipate. That information comes directly from this one. Initially, this free ligand shows only 2 signals, singlets, and then when you make a platinum complex, now both the phosphorus are coupled apart from coupling to platinum. I have shown here, you can see here, PN bound one is shown here, and whereas this is for PO bound one. And then they are also showing the satellite as expected, because this, whatever the doublet is there, major doublet, this is for 66% 196 platinum, I equals 0, and then the corresponding one is here and one is here. This coupling is 3933 Hertz, and this is 1J PT P coupling here, and 1J PTP coupling is 3933 Hertz, and in case of PO it is 4066 Hertz are there, and then the PP coupling is 13.3 Hertz here. And this is again interesting molecule here. You can see the structure it has a puckered chelate ring. You can see here now they are coupled through space. One more example is there here. Just look into this molecule here. This is a cationic complex. We have three different type of phosphorus atoms are there, and all of them are coupled with each other because they are all 2 bond apart. So now again interpretation is also easy here. Just if you see here, all are different. So you have something like AMX spin system here. This phosphorus couples with first this one trans, and then it gives doublet of doublet, and then similarly this one would couple with this one, or this one doublet of doublet, and this also couples with doublet of doublet, because all are in a different chemical environment is there. You can see each one is showing a doublet of doublet, a typical AMX spin system. So in case of AMX spin system, and also the field strength is very high, it does not show any second order splitting here. Second order splitting is invariably observed in case of 1H NMR, where we have 2 hydrogen atoms present on same carbon. The geminal coupling will be seen. The carbon is substituted with different groups on either side. So now let us look into one interesting reaction here. This ruthenium compound, I am sure you know the structure of it. This is a tetrahedral molecule with ruthenium in +2 state. You can also do electron counting for this one. If you do by neutral method, this is 8 plus 5 for CP group, and this is for 1, and this is for 2, and this is for 2. This is a 18 electron complex, 14 plus 16 plus 18, and this is by neutral method. By ionic method also we shall do this. Ruthenium 8 means 6 are there, and this is giving 6 electrons now, and this is giving 2 electrons now, and both of them are giving 2 electrons each. This is 18 electron. So this is the 18 electron system. When it is reacted with this PNP ligand, what happens? We are getting lot of different type of compounds are there here. Okay, for example, you can see here when it is reacted, it gives a mixture of compounds here. It gives a mixture of compounds. One is a chelated compound replacing 2 triphenyl phosphines, whereas here it becomes a cationic complex here. 2 PPH3 and Cl also has come out, and then one chelation and one acting as a dangling monodentate ligand. In other one PPH3 is there, and so all these 3 are formed here. Once all of the, how do we know that all the 3 are formed? Simply by looking into the 31p NMR spectrum of the reaction mixture. That reaction mixture also gives in what ratio these compounds have formed. Once we know that in what ratio these compounds are formed, whether it is possible to prepare those compounds in pure form by varying the stoichiometry and varying the reaction condition. For example, if this you take this compound here, and then ruthenium to chlorine bond is ionized, that means if I use a polar solvent and you prolong the reaction, it is likely that I can form a cationic compound, something like this. Or if I use excess of phosphine, bisphosphine, one can get like this. But by controlling the stoichiometry, if you use 1:1 reaction in a polar solvent, you can get this one. That means this kind of vital information one can get simply by analyzing the spectrum of reaction mixture, again using very simple 31p NMR spectroscopy. So let me show you the spectrum for this molecule in my next lecture. Very interesting. And also, how did we come to conclusion about the spectrum analyzing this particular set of multiplets for this molecule? That of course, when we carried out individual reactions also, separate reactions and isolated compounds, we can confirm. And in some cases it's very simple, whereas in this case it's very simple. You should get a droplet and a triplet that is there, and then in this case you can get a singlet, and so there is no scope for any confusion. But if there is any scope for confusion of having similar pattern for 2 or more molecules, then we have to separately make them and confirm their chemical shifts. Okay, let me discuss more about this one in my next lecture. Until then, have an excellent time. Thank you so much.